unlike combinations, compositions is a little more complicated. What we're doing instead is we are sticking one function inside of another. Okay, we're going to illustrate this in a couple of different ways. We're just going to start with some numerical things. So let's see, just a couple things to talk about here. In the notation, which is commonly referred to as fog and goff, it's not the letter that matters, it's the position in the symbol that matters. So we've got an inner function. If I can get this going here. If I get an inner function and an outer function. So in that notation, G is the inner and F is the outer. And we're going to switch places back and forth, so it helps to note just where it is in the symbol. So in this first question, f of g of 0, I'm going to start by finding the inner number. So I want to know what g of 0 is. So go to the g function and evaluate it at 0. So 0 squared minus 2 gives me negative 2. That thing I am then going to stick inside f and evaluate. So f of negative 2, which would be negative 2 plus 3, which is 1. So f of g of 0 is 1. Okay, now we can switch the order, and we're not guaranteed that it's going to be the same answer, and you'll kind of see why here in a second. So we have f of 0, which is x plus 3, so 0 plus 3, which is 3. And then g of 3, which is 3 squared minus 2. And that would give us 9 minus 2, which is 7. Okay, so we get two different values. In other words, order matters. We do have to pay attention to which one comes first and second, and that sort of thing. Okay, we're going to do a sort of a symbolic approach to this. F of g of x. So I want to take g of x and evaluate it inside f of x. So f of g of x means take the g function, which is x squared minus 2, and evaluate it in the f function. So that would be x plus 3. So we're going to take g and add 3 to it, and then simplify this down. So that would be x squared plus 1 would be f of g of x. You can also do f of x. So you can stick f inside itself. So I want to take f, which is x plus 3, and I want to evaluate it inside itself, which means I just want to take x plus 3 with another plus 3. Okay, which in this case is just x plus 6. Okay, we can also do the same logic with a table. So there's an inner and outer piece here. So I'm going to start by finding the inner. So g of negative 1 and g of negative 1 is 1. And then I want to find the value of that in the outer function. So I want to find f of 1. So f of 1, go over my chart, happens to be 1 coincidentally. So that would be f of g of negative 1 is equal to 1. I can also do f of negative 1. So start with the value of f of negative 1, which is 0. And then I want to find f of 0, so take the inner y value, I guess, and substitute it back in the outer. And so f of 0 is negative 2, so we get that. We're going to keep going here. G of 2, so g of 2, we end up with 0, and then I want g of 0, which oddly enough happens to be 0. And then f of g of 1, so again start with inner, g of 1. So go over the chart, g of 1 happens to be negative 1. And then I want f of negative 1. And f of negative 1 happens to be 0. Okay, so the last sort of skill we can do with composition is we can actually make the composition functions in an algebraic sense, meaning keep it in terms of x. And then we'll talk about the domains of how those things work. So let me first tackle making the function, and then I'll come back and make a statement about how to find the domains of these compositions. So we're going to do f of g of x and g of f of x together. We'll do f of x first, and then we'll come back and do g of x. So In this case, f is x squared plus 3 and g is 2x minus 1. So if I want f of g of x, I want to take the g function and insert it inside the f function. So be something squared plus 3, and I want to put g inside that, so 2x minus 1. And then we'll just simplify and combine like terms. So if I FOIL out 2x minus 1, I get 4x squared, let's see, minus negative 2x, double that, so you get negative 4x plus 1 plus 3. And the only thing that can combine is the 1 and the 3. So 4x squared minus 4x plus 4. Okay, let's talk about domains then of compositions of functions. In a domain, any restriction that showed up on the inner function is going to show up on the composition function. So the idea is you figure out domain restrictions of the inner, then you make the composition, and you figure out domain restrictions on the composition. Okay, and the logic behind that is, in the inner function, if it has any restrictions, so say a number doesn't, 7 doesn't show up for whatever reason, when you make the composition function, 7 didn't show up to begin with, so it wouldn't show up in the composition, even if we don't necessarily see that. Now, in number 9 here, we're not going to see exactly what I'm talking about. Number 10 will be a stronger illustration of what I mean by restrictions that don't show up. But the restriction of g is all reals, as it's a 2x minus 1, there's just polynomial. And then 4x squared minus 4x plus 4 is a polynomial. So there's no restrictions on either one. So our composition domain would be all reals. Okay. Let's switch directions. Let's go g of f of x. Okay. So this time I want to take f and insert it inside g. So 2 times f minus 1. And I'm going to switch colors here. That would be x squared plus 3. And then I'll distribute and simplify and combine like terms and all that. So that'd be 2x squared plus 6 minus 1. So that's 2x squared plus 5. Okay. And then as far as domain goes, were there any restrictions on x squared plus 3? Nope. It's polynomial. It's quadratic. No restrictions on it. And then any restrictions on 2x plus 5? No, nothing. It's not a fraction. It's not a square root. So the domain for this is all real numbers. Okay, so number 10, we're given x squared minus 1. And let's just take a second and talk about domains of each function. So in x squared minus 1, the domain of that is going to be all real numbers. There's no restriction on it. However, in the square root of x plus 1, we have, see, negative 1 being a critical point. I think we've seen this example enough times in this review session that I'm just going to jump to the domain being negative 1 to infinity on that. Can I rewrite that? Okay. All right, and I'll kind of leave that hanging out there, so when we talk about restrictions on the composition, we can reference this initial domain. So let's start with f of g of x. Try that again. F of g of x. Okay, so inside the f function, I'm going to stick the g function. All right, so if I square a square root, that cancels out the square root, and I'm left with x plus 1 minus 1. Okay, and then plus 1 minus 1 leaves me just with x. Now what about its domain? Well, x itself doesn't have any restrictions. That's all real numbers. But if you remember, the rule with compositions is whatever didn't come to the party of the inner, it's not going to come to the party of the outer. So the domain of square root of x plus 1 is still this negative 1 out to infinity with the bracket there. The composition didn't add anything new to that, so that domain stays right where it is. It's still negative 1 out to infinity. Okay. Let's switch directions. I go g of f of x. So square root of something plus 1. Let's see. X squared minus 1. And then we want to add that plus 1 back in. Okay. Well, square root of x squared plus minus 1 plus 1 gives me square root of x squared. And square root of x squared gives me x. And let's talk about domains. Okay, so we're going to go to the inner. The inner did not have any domain restrictions. X squared minus 1 doesn't have any limiting numbers. It's going to be all real numbers. And when I made the composition, I got x. X also has all real numbers. So the domain of this function, this composition, would be all reals, negative infinity to infinity. Okay. Okay, number 11, we're going to start with that same idea of what restrictions are already built in to each function, and then we'll kind of remind ourselves of that as we make the compositions. So for number 11 here, for f, 1 over x plus 1, I'm just going to write myself a little note that the domain is that x can't be negative 1. If negative 1, I'm dividing by 0, and that's not good. For g, I'm going to make myself a note that x can't be 3. And I'll come back and refer to these later as we make our compositions. So I want f of g of x. So I'm going to take the x function and insert it into the f function. So it'd be 1 over, and then we'll go x over x minus 3. Oops. X over x minus 3. And then I want to subtract out or add that plus 1. Okay, so I'm going to take advantage of some common denominator rules, and I would like to make everything, and I mean everything, have a common denominator of x minus 3. Okay, so up in the numerator we'll have, we'll leave that as a 1. We'll have x over x minus 3, and we're going to make this one say x minus 3 over x minus 3. And then I can combine the two fractions in the denominator. So that's going to be 1 over, that denominator is x minus 3. Well, if I combine like terms, I get 2x minus 3. And remember your rule with fractions, if you divide by a fraction, you multiply by its reciprocal. So this works out to be x minus 3 on the numerator and 2x minus 3 in the denominator. Okay, now what new restriction did this statement pick up? Well, we're still dealing with fraction rules, so we're still looking at what's going to put 0 in the denominator. And we notice that we cannot have, in the domain of this one statement, we can't have x equal to, let's see, positive 3/2. If x is positive 3/2, then we can't, we get 0 in that composition. Okay, so what about my overall domain, my domain of the composition? Well, I can't have 3/2, and I add into it any other restriction from the inner function. So the inner function was g this time, and g said I can't have 3. So I want to say I can't have 3/2 and 3. So I'm going to go from negative infinity up to, well, what's the next number? Is it 3/2 or is it 3? 3/2 is 1.5, so 3/2 is next. Union 3/2 to 3, union 3 to infinity. So kind of a longer statement, but all we're saying with this is that I can have anything before 3/2, anything between 3/2 and 3, and anything after 3. Okay, so let's go the other direction. Let's do g of f of x. All right, so g of f of x. So anywhere there's an x, I'm going to write 1 over x plus 1. So 1 over x plus 1 over, then I want x minus 3. So 1 over x plus 1 minus 3. Okay. And I want to make everything have a denominator of x plus 1. So in the numerator, that's already set up that way. Denominator's got part of it set up that way, so 1 over x plus 1 minus 3 times x plus 1 over x plus 1. And now everything's got the right denominator. And then I'm going to combine like terms and simplify where I can. So 1 minus 3x minus 3, which is 1 over x plus 1 over negative 3x minus 2 over x plus 1. Okay, and then we use our fraction rule, so we have 1 over x plus 1 times x plus 1 over negative 3x minus 2. Okay, and what do you notice? You notice the x plus 1's divide out, and so our composition is 1 over negative 3x minus 2. Okay, well, that's off screen. What restriction does this new fraction have? We can't have x equal to negative 2/3. So if x is equal to negative 2/3, I'd get a 0 on that. Okay, so going back up to the initial, the inner function couldn't have negative 1. Outer function can't have negative 2/3. So that's what I want to say. I want to say everything but those two numbers. So my domain would be negative infinity up to, well, which number do I hit first? Do I hit negative 1 first, or do I hit negative 2/3 first? Negative 1 is smaller than negative 2/3, so I'm going to hit that one first on the number line. Negative 1 up to negative 2/3, union negative 2/3 up to infinity would be the domain of that particular statement.